word equilibrium a couple times. I mean, I have. I don't know if you're listening or not. So far in this class. But most of the time when we have looked at chemical reactions so far, we've only been looking to the forward reaction of what's written down, where we assume that the reaction proceeds to completion, meaning that one of the reactants will run out. But there are many reactions that do not run to completion. So one example of this is limiting reactant reactions have an amount of excess reactant left over with the products. And so when you have that leftover reactant, technically it's not run to completion since there is some reactant left over. So equilibrium helps us to see this. Other reactions that stop short of running to completion. So chemical equilibrium is a state where concentrations of all reactants and products remain constant with time. So when you reach chemical equilibrium, you can no longer see a change in the chemical reactants or products, but they are not, there is a high state of dynamic reaction happening. It's just to our eyes, we can't see it anymore. So, see, I'm already confused. Gosh. Some of our observable processes are reversible. So some examples of physical changes would be phase changes, like for example, condensation versus evaporation. That phase change is reversible. Adsorption versus desorption of a gas when it's created, when it is going away. Or the dissolution or precipitation of a salt. So when you're dissolving an ionic compound into water, how well can it be dissolved? Or does it precipitate from, so does it stay solid form, I guess. So some of these physical changes are reversible, where we can have both changes occurring at the same time, or one could go one way and the other could go the other way. Some chemical reaction examples would be the transfer of protons in an acid-base reaction. Acid and base reactions happen by transferring H pluses, that's what are protons, in this wording. And then electrons and redox reactions, which we have talked about redox this year. So when we have electrons transfer, usually in single replacement reactions, then we can have the reaction take place. But most are reversible. So that means that you can go forward and you can go backwards for them. So because no changes occur in the concentrations of reactants or products in a reaction system at equilibrium, it may appear that everything is stopped, but that's not true. On the molecular level, equilibrium is a highly dynamic situation. So it means that to our eyes, we can't see changes, but at the actual level, we were able to see the molecules and the atoms changing. They would be constantly changing. It's just the rates are equal to each other. So this picture is in the textbook on page 609. And so this shows how a reaction might take place over time, where the A would be at the beginning. This is only reactants, because if you notice, it says that time increases that way as time progresses that way. So then our two reactants, does anyone take a guess at what those two molecules are? Yep. This one's water. What do you think this one is? Carbon monoxide. Yep. Carbons are usually darker, black ones, and then the red for oxygen, so that would be COs. So the reactants for this reaction are water and carbon monoxide, okay? And so in A, this is before the reaction takes place, okay? But then as the reaction starts, we start creating products. So what do you think that product right there is? Yep, that would be H2. And then this right here is another new one. That one would be CO2. So the reactants are H2O plus CO, and then the products would be CO2 plus H2. So eventually we have this forward reaction happening. So as we see into C, there's more hydrogen gas and more carbon dioxide formed, less H2O and CO left in the box. But then eventually, like, so if I'm counting, I guess, at some point, even though we have the turnover, it's constant. This is the same, basically, if you try to count up the molecules, you have the same numbers. Like, there's 2 waters in each box, and there's 1, 2, 3, 4, 5 CO2s. 1, 2, 3, 4, 5. So this just says that it's going to be constant over time. There's no longer any change, even though we still have reactants left over. Okay, so they are both present. So if it's constant over time, that means that maybe we created way too much product, and so we had to go back and reform some of the reactants. And so that reversible side of things is when you can go backwards like that. Okay, so the way that we show, this was just a way to show by molecules how we can end up being constant over time. But a lot of times you might have to look at graphs to help you determine this. And so when you look at a graph, this one has, you have to be careful, X and Y axes. So this is time for the X versus concentration, okay? So this is for that reaction we just saw, where the green that starts up high for concentration represent the 2 reactants. And then the one that starts at 0 represents the products. Okay, so it makes sense that at the beginning, in that first box, A, we did not have any products, we only had reactants present, right? But then as time progressed, the amount of reactants goes down, and the amount of products starts to increase. And so then the way that we know that we've reached equilibrium is when the amounts of both the reactants and products even out. They become parallel. Okay? So when they are parallel, then that shows us that we are at equilibrium for time versus concentration. The concentrations are not equal. That is going to be like a trick question on a quiz. Concentrations are not equal. What's equal is they have evened out. They're no longer changing. There's no more change in concentration. Does that make sense? Okay. So I like to look at the graphs because it really helps me, and it might help you to think about that. So even if you have a multiple choice question and ask something about this, think back to what this looks like and draw yourself your little graph, and it might be helpful. So that was all of the first section, right? Did everybody see my joke? I'm sure glad they evaporated. We're back. Now I'm getting out of here because it's vapor pressure and the molecules are evaporating and recondensing. Equilibrium. Jokes. Yeah. Okay. 7.2. So for 7.2, this is all about how do you know which reaction is more favored? So when any chemical reaction is carried out in a closed vessel, like my joke, it will eventually reach equilibrium. So sometimes the reaction will favor the products. And a lot of times in Chem 1, this is what we see. We only see products from a reaction. So it appears to us that the reaction has gone to completion. So when the products are favored, we say that the equilibrium position lies far to the right. Right literally meaning the right side of the arrow for the products, in the direction of the products. And then this type of reaction would be the forward reaction. So you just want to make sure that you are paying attention to that the products are have the position to the right, and that is the forward reaction, which up until today, we've only talked about the forward reaction. So, for the most part, except we did do the reverse reaction when we were doing something. I don't remember what it was now. Now, when it favors the reactants, then it appears to us that no reaction has taken place. So in Chem 1, when we do a bunch of tests, it might say, like we might have just said no reaction if it doesn't look like there's any change. Well, that's because the equilibrium lies far to the left, meaning that it actually favors the reverse reaction. So if the reaction we were looking for lies to the left, in Chem 1, we should have put the products together instead of the reactants, and then we might have actually seen some change. But in Chem 1, that's like over your head, so we don't do that. We just say that there's no reaction. But if it favors the reactants to us in the lab, it might look like nothing happened, but that's because the reactants are favored. So this is another graph that I really enjoy. It helps me. If you have time on the x-axis, and then the reaction rates. So we talked about reaction rates with our kinetics last unit, I think, where if you have a forward and reverse reaction, the rate of the forward reaction is going to start out very high if you only have reactants present. So if we think back to in the 7.1 example, we only started with reactants, so there's nowhere else to go except to the products, to create products. And that's why the reverse reaction rate is 0 to start, because there's no products. But then as time progresses, eventually the rates will equal each other. So at equilibrium, the rates are equal to each other, not the concentrations, the rates. The rate of the forward reaction is equal to the rate of the reverse reaction. And so this graph shows that when the two rates form together into one line. Okay, so these graphs are just supposed to help you figure that out. So rates are equal at equilibrium, not the concentrations, not the amounts. And so then, even though it looks to us like there's no longer any change, if the rates are equal to each other, there is actual change. It's just the processes are happening at the same time. Okay?